Hello. Hi guys, good morning. Welcome back to the new video. And I know for sure there has been quite a lot of delay between the last video in which we saw bipartite graph and topological sort and this video. But yeah, I know we have been giving in more videos related to other topics and stuff, and also contest live streams and a bit work. So it's hard to catch up on everything. But yeah, we have done. I have made the notes of 2-3, so for sure these will be coming in and we'll try to finish this as soon as possible. Cool, let's go quickly on the problem statement. Shortest path in a directed acyclic graph. Please make sure that everything matters here. What we are finding, firstly, if you don't know, it's lecture 21. If you have not watched the previous lecture in which we have spoken about the topological sort, and specifically when I say we have taught it, we actually mean by the intuition behind how to think that topological sort is even gonna be applied in XYZ problem or not. That is the specific USP of our videos. Going back to what it says is shortest path in a directed acyclic graph. Now, directed, which means the graph should have directions. It should not be undirected, or if it is undirected, it can still have the answer, but still here in this video we are finding the graph should be directed, which means this directed edge should be there. Cool. It should be acyclic, which means the cycle should not be in the graph. Aryan, shortest path, I have heard something like, okay, single source shortest path. For sure, when you are saying you will start the problem and find the shortest path, for sure you will be finding the shortest path from some of the source, which means the source will be one. So I have heard of single source shortest path, a single source shortest path problem, and I always remember that someone has told that Dijkstra can be applied. But if you know that Dijkstra is a O of n log n kind of algorithm, or O of V log V kind of algorithm, and here we are saying we can solve this in O of n, provided the Dijkstra's can solve this if it is even cyclic, but I can only solve it when it is acyclic. That's the reason. Please don't be confused when I say it is a single source shortest path problem, but for a DAG and not a cyclic graph. Dijkstra's can solve you for the cyclic graph also, but in this we are going to see for the DAG, and that's the reason. Although the same problem can be solved with Dijkstra's also, but we are solving it more efficiently, which means we will be solving it not O of n log n or O of n plus e log n or something like that. We will solve it O of n plus e, which means in the linear time we will try to solve it, and that's how the specific part is. Okay, it is better than that of Dijkstra's in terms of what is asked to us. We are asked to find in that season specifically. I specifically force quite a lot on why this problem name is itself important, because any problem can be solved by many ways. By a simple DFS, BFS also you can solve the problem, but still there's always a catch on how to solve it more efficiently. Now I know that the problem is to find the shortest path in a directed acyclic graph, where acyclic is very important and shortest path is what we aim to find. Simply say, okay, if you are from a city A to any XYZ, let's say I want to travel from Bangalore to Delhi, I have multiple hops in between. I know that hops, if I land onto any hops, it will not form any cycles. So that's a real life use case that we can apply this in the least complexity, which means we will try to solve it in just O of V plus E or O of n plus E kind of complexity, which means the linear time. Now again, you can have any source, but here for our simplicity we can start with our source as 0, but you can take the source as anything whatsoever you want. Now problem, as we have a directed graph, as you can see, it is not cyclic because you cannot find any cycle at all. Right? Any cycle at all you cannot find in this entire graph. For sure, it's a directed acyclic graph. Now my task is to find the shortest distance from the node 0, although here I say a node 0, but you can choose any node as a starting node, and from that node you can find the shortest distance too. Cool. I'll try to find the shortest distance from node 0 to every other node in this graph, and it is nothing which new I have made. I have just grabbed the exact same problem as given in the example itself. Now you see, I see that the problem is vector of vectors, where each vector inside this entire list of vectors is actually saying, okay, I have a source node, I have a destination node, and I have a weight. I have a source, I have a destination, I have a weight. So with this vector of vectors, I will simply make an adjacency list, because I know that the graph we traverse in the form of the adjacency list, right? So with this entire stuff, I will try to make so as to process the graphs. Although you can also process the graphs in this way, but we have standardly seen how to process the graphs. We process the graph in the form of an adjacency list. So what I will do is I will just simply say, okay, node 0, I will have a simple list of vectors saying, okay, node 1, it is going to node 1, as you can see, node 0 to node 1, and the weight is 2. Okay, weight is 2. Another is node 0 to node 4. Okay, node 0 to node 4, and the weight, node 4, and the weight is 1. Cool, the weight is 1, and so on. I can make it for every other node. So that is how I can build my adjacency list. Okay, now let's say my graph is built, which means my adjacency list is built. Now my main task is to find the shortest distance. Now you see, I see, please don't read the right part. Let's see quickly, just take a step back and see what we can think of. If I just want to find, okay, shortest distance from 0 to 2. Cool. I can go in from here. Okay, the distance is 2. I can go in from here. The distance is, okay, 5. Oh, although, okay, if I would have grabbed the distance, okay, it is 1, then I would have grabbed this distance, okay, it would have been 3, cancelling this 5. Oh, you saw one thing. To reach this 2, there are two possibilities. Either I come from here or I come from here. Or we can say is, there are two possibilities. Either I come from here or I come from here. Now, to reach this particular one node, I have only one possibility. I will come from here. To reach this node 4, I have only one possibility. I will come from here. So, when I was saying I will find the shortest distance up to 2, wasn't it good to imagine that, okay, everything before 2 should have been processed, right? Which means, okay, when I am trying for the number for the node 2, I should be making sure, okay, everything before it is processed so that I can process node 2. Which means if I would say, okay, let's say the node 4 is not processed. So node 2 would be assuming, okay, the shortest distance up till 2 is 5, and it would give the other node 3 as the shortest distance 11. But if I say, okay, if I process the node 5 also, which will say, if I process the node 4, it will just give me shortest distance up till node 4 is 1. Shortest distance up till node 5 is actually 4. Sorry, it is actually 5, because 1 plus 4 is actually 5. Now, shortest distance up till 3 would be nothing but earlier it was imagining the shortest distance is 11. But no, it is not. It is actually 5. So what we figured out was, in the shorter example here, that it is always good for 2 that, okay, everything before it should be processed. Now, if you had remembered the same statement as we saw it in topological sort, the specific use of topological sort is a simple BFS, but provided a fact changes that everything before it should have been processed. I can go on to node 2 only and only when everything before it is processed. Now, this is something which is the main thing that why we use a topological sort. This statement, if ever you encounter it, if you're landing onto a node, but if you think everything before it should have been processed, this statement is itself indicative of the fact that you have to apply a topological sort. Now, so we know, okay, to process this node 2, for sure everything before it should have been processed, which means shortest distance up till the node 1 should have been there. Shortest distance up till node 4 should have been there. Now, when it is there, what it will try to do is it will just try to say, okay, if I just am the shortest distance up till the shortest distance is 2. For node 1, the shortest distance is 2. So it will just say, okay, if I just go on and give it forward, it will just give you as 5 the shortest distance. This node 4 as shortest distance 1 will say, if I go in forward, I will give the shortest distance as 3. So I just keep on taking the minimum, and whatsoever minimum I get, I'll simply grab it. Now at 2, when I am at 2, I will know for sure the shortest distance up till me is actually a 3, because before me everything has been processed. And how I made sure? I made it sure with the help of a topological sort. So you know how you backtracked it. You got to know, okay, if I am at node 2, I should make sure everything before me is processed. Now whenever I say the statement that everything before me is processed, I am saying directly that I should apply a topological sort. When I am applying a topological sort, I will just directly apply that in this manner, okay, in the order of topological sort. Every node I am processing and just giving in the shortest distance to the next person. Now up till 2, the shortest distance is actually a 3, right? So it will give in the shortest distance next node as 9. But you also know up till 4, the shortest distance is actually a 1. So it will process and give it, okay, next to me, the shortest distance will be actually a 5. Cool. For 5, everything is processed before it, so it will give the shortest distance to the next person as 6. So for this, the minimum will actually be a 6. So now when I will say for 3, everything before it is processed, I am giving in the shortest distance to the node 3. And that's how you can simply get this solved. Now, how to find the topological sort? If you have not seen it, we have taught the same thing in graph lecture 16 and 18. It is lecture 21. So if you just go and have a look, graph 16 will be a BFS. If you want to find the topological sort with the help of a BFS, it is a lecture 16, and 18 is nothing but DFS. Both are simple and easy. More intuitive is 16, lecture 16, which means topological sort with the help of a BFS. But you know, BFS is a bit lengthy code. But if you are much familiar with how it works, you can just go on and switch to DFS. Simply just saying how a DP problem works. With memorization, it is easy, but with top down, it is a bit hard, but shorter code. That's the same goes for a topological sort with BFS and DFS. Cool. Now, so what we saw, we can solve single source shortest path problem provided it is on directed acyclic graph. Acyclic is the most important word in O of V plus E time. But you know O of V plus E. Why? If you don't know, then it's a simply same complexity as that of a topological sort. Simple, right? But if you don't know, this can also be solved by a Dijkstra's, but still Dijkstra's has more complexity. Why? Because it can also be solved for a cyclic graph. Now, I saw that why we need to solve this, why we need to apply topological ordering, because we are processing the node sequentially. Why sequentially? Because for any node to get the shortest distance to it, before that node, all the nodes should have been processed. Now, just simply bringing it back, as we saw that for the node 2, everything, which means node 1 and 4 should have been processed, because it is giving in 5, it is giving in 3. So minimum would actually be giving in when everything before it is processed. That's the reason we actually applied a topological sort. Now simply a dry run of how it can be done. So firstly, we will be using a topological ordering via DFS. Although I have already spoken, BFS is the most intuitive way, but still we will be choosing a DFS way because the code is very, very, very short because of DFS. Now, if you don't remember, a quick walkthrough of how a topological ordering via DFS works in, we simply start from any node. We will keep on going until I am at the end of the node, which means I cannot go further, which means, okay, nothing is after that. Okay, I'll just start from 0. I can go in on 1, but when I say I start from 0, I actually mean the node 4 is actually on waiting. So when I say the node 0 is done, I will mean node 1 is done and node 4 is done entirely. But you know, node 4 is on waiting for node 0. So node 0 cannot be done until the node 4 is done. It is how a DFS works in. When I call in a DFS at 0, it will call in a DFS at 1 and 4, which means all the neighbors of 0. Cool. But still, it will just go in the depth wise. That's the reason specifically it will just entirely try to go in, right? Now, coming it back, okay, it will just go on to 1. Cool. It can just only go to 2. Cool. It can go to 3. Cool. After 3, it cannot go. So simply it will just push in the 3. Okay. The 3 is done. Cool. It will come back after 2. Can it go anywhere after 2? Which means it has any other edges? No, it does not. Okay. Also, R2 is done. Cool. R2 is done. Now it will just come to 1 because a simple how a DFS works. It will just simply come back. It will just try to come in. Okay. From 1, it will just start to say, okay, can I go somewhere else? No, it cannot. So simply, okay, R1 is also done. Okay, 1 is also done. But 0 was still there. After 0, I can still have a DFS at 4. So okay, it will try to go in 4. After 4, it can go to 2 also, but 2 is already done. Already done. So please don't visit that. Go to 5. Okay, 5, I'll go. Go to 3. Oh, the 3 is already done. Please come back. Okay, I'll just simply come back. Okay, 5, I'll come back. Cool. 4. Simply, okay, nothing is there. Okay, it is also done. It is also done. Cool. Come back. Okay, 4 is also done. Come back. Cool. For node 0, everything is done. Simply come back. Okay, cool. Simply come back. So the topological ordering for this entirely, as I have just pushing in like this, so topological ordering is nothing but the reverse of it, which is 0, 4, 5, 1, 2, and 3. Now you say, Aryan, it was simply straightforward. But yeah, if you had remembered the ordering, I'll just go and highly recommend go and watch the lecture. But if not, then let's quickly have ordering if we would have started from node 0 itself, but if we would have gone at node 4. Let's say if I would have gone, or let's even imagine, okay, I start from the node 4. Cool. I'll simply, or maybe any node you can choose. In ordering, you can choose any node. It's just that you will have to do this ordering on every node. Let's say I start from here. Cool. Earlier I went on to here. Let's say I went on first to here. Cool. Again, I have two options, 2 and 5. So I can go in anywhere. Let's say I went to 5. Cool. I went to 5. Again, I have only one option. Okay, I'll go to 3. Okay, it's done. It's dead end. Okay, cool. It will simply try to come back. Come back from 3. Okay, 3 is the last one. 5. I cannot go anywhere from 5. Okay, cool. Come back. Okay, it's 5. From 4. 4 is not yet done. I can simply again go on to 2. So please go on to 2. Okay, now 2. I'll try to go on from 2 to another node. Okay, 3. I cannot go. It's already done. So cool. Simply come back. Okay, cool. It simply come back. Cool. 4. Oh, I cannot go anywhere. Both 2 and 5 are done. Cool. Simply come back. Okay, 4. Simply come back. Cool. Other node from 0, it's still not done. 1 is still remaining. Okay, cool. Go to 1. From 1, I can go to, okay, but it's already visited. Cool. Come back. Okay, 1 is done. Come back. Ultimately, I'm done. Come back. So it is another topological ordering. I just want any one ordering whatsoever. You can have many orderings. So it's just one such ordering again. 0, 1, 4, 2, 5, 3. You saw what's happening. I am using in from here, right? I have to simply reverse it down to actually have the correct ordering because I am pushing in the elements in the reverse order. Now, I know that we have got the ordering to us, which means I will have to process the elements in this order itself, which means I have this ordering. I will have to, although you know that when we are storing the ordering, if you use stack, vector, anything whatsoever, we are pushing in the elements. So if I'm just grabbing the elements out, I will just grab in from the end. If I have the stack, I will just grab the stack top. It is how it is work. But let's say if I just reverse it down and got this entire thing, I have this as the top, which means although if you just have the entire stack, you will grab the top of the stack. But if you have, just imagine like a vector and you have this vector of your ordering. Now you will process this in the same order, which means I will process this as 0 first. When I say I process, I know I am starting from this node 0. So the distance is actually a 0. Now to the next node, I'll just process to the next node, which means from 0, I can go anywhere I try to go and try to minimize. When I say minimize, I just relax those nodes. Relax, which means, okay, minimize them or maximize them. It is needed to minimize. It is saying give the shortest distance. So I'm minimizing or relaxing whatsoever they could have. So from 0, I will just try, okay, I am at 0. And for sure, it's a node which I should be at and I am at. I'll try to relax everyone from whom I can reach. I can reach my neighbors, so I'll relax my neighbors. I'll relax node 1. Okay, it's a 2 distance. Okay, 2 distance. I'll relax node 4. It's a 1 distance. Cool. It's done. Now, node 0 is done. Cool. Now, my next node I have to process is a node 4. Cool. Node 0 is done. Node 4 is the next node to process. I'll process the next node. From 4, although if you go via this node, you can also process node 1 first. Anyway, any ordering is correct. If I process the node 1, cool. Sorry, node 4, what will happen? It knows my distance up till me, shortest distance up till me is actually 1. So for sure, if I am relaxing my neighbors, I will be relaxing my best possibility to them. I relax my best possibility to my next neighbors. It will try to relax the next neighbor, which is 3. It will try to relax the next neighbor, which is actually a 5. Cool. It has relaxed node 2 and node 5 with the values 3 and 5, which is the best possible which 4 could have given. That is the reason we are relaxing in order, because we want everyone to impact its neighbors to the best possibility they could have impacted. Now, okay, cool. 4 node is done. 4 node is done. Now I can relax node 5 with my order. Okay, I will relax node 5. From 5, I can relax my neighbors. Cool. And you know, it is done. It is done. Cool. Which means they have relaxed their neighbors. 5 is the turn of 5. 5 will try to relax its neighbor, which is 3. Cool. Relaxing with the weight as 6. Okay, cool. It is done. 5 is also done. Now, next chance is actually of 1. Cool. 1 will try to relax. It is done. It is done. It is done. 1 will try to relax its neighbor. Its neighbor is actually having a distance. It has a distance which is the minimum distance to it is actually 1. It will try to relax its neighbors with the distance of 2 plus 3 as 5. But it already knows my neighbor already has a distance of 3. So it will just take the minimum. Okay, 3 it already has. 5 I am giving. Okay, minimum is 3. Okay, so value is 3, which means it tried to relax its neighbor, but his neighbor was already minimum, so it did not reduce the value. Cool. Now 1 is also done. Cool. 1 is done, 0 is done, 4 is done, 5 is done. Next chance is of actually a 2. Cool. I just simply use 2 and try to relax its neighbors, because up till 2, the distance, minimum distance up till 2 is actually a 3. That is the truth. So for sure it will try to relax its neighbors by a distance of a 3 plus 6, which is actually a 9. Cool. Getting the minimum value, which is simply a 6, because earlier it was having value 6, but it tried to relax with the 9. For sure it will just start with the minimum itself. Minimum is actually a 6. Okay, cool. I have got the minimum value as 6 itself. Now, I know that, okay, I have got everything as the minimum, because it is also done. It is also done. So everything, it has a distance 0, it has a distance 2, it has a distance 1, a distance of 5, a distance of 3, a distance of 6. We have got from the source node the minimum distance to every node, and that is the ultimate thing, which means step 1, simply find the topological sort. You can simply find it via a DFS or a BFS, anything whatsoever you want. Here the code is short of DFS, so maybe we can write a DFS, but still it's totally up to you, because BFS as a topological sort is actually more intuitive. Now coming back, okay, when we have found, just simply go in the order of that DFS or go in the order of that topological sorting and keep on relaxing the neighbors of that particular node. Which means if I am at this node, it means for sure if I am at node 1, anything, the node 1 is storing the minimum value up till that point. So simply go and relax with the help of node 1. Go and relax its neighbors, because 1 will give it the minimum value to its neighbors itself. Cool. Now with this, by what I will know, okay, I will have the shortest distance from the source node to every other node ultimately, and for sure here the weights can also be negative, so that is a one big thing for us. So the benefit of using a single source shortest path in a directed acyclic graph with weighted edges. Now here, if the Dijkstra's cannot solve it if the weights are negative, although it can solve it if it is cyclic, but cannot solve it with the negative weights. So if you have negative weights or positive weights and it is acyclic, then the best algorithm is the one we showed here. Cool. Now going it back, and that's the reason I specifically mentioned about Dijkstra's here, not to confuse you, but because ultimately when you will reach on Dijkstra's, or you must have heard by someone, because it's a very, very, very famous algorithm, you must have heard of it. But if you have, then you must be confused. Okay, why I'm not applying Dijkstra's here? That's a specific reason why you're not applying Dijkstra's here, and why this cannot be applied when you apply a Dijkstra, because it is applicable on a cyclic graph also, while this which you are learning here is not. Because why it is not? Because the topological sort, this thing, it is only applicable on a cyclic graph, right? That is the reason I cannot apply this method, because in this, the prime USP of this problem is finding the topological sort, and the intuition to find it, we have seen it now. Cool. Going it back, how we will simply solve it? We will simply solve it firstly by simply converting our edges to actually a adjacency list, as we have seen. And how adjacency list? With the actual node U to to the node V and the edge weight W. Now we have converted our directed graph to the adjacency list. Now we will try and find the topological sort simply as I have shown above, simply going in the entire DFS and in the end just pushing that node in my particular stack. And as we have done, as you will simply do it for every node, which means I can start from any node itself, right? So that's the reason I just go on from every node and will do the entire topological sort so as to just get the entire topological sort of this graph. Now, when I have got it, I will simply have to maintain a distance array, initialize with the maximum value because I want the shortest distance here. Now distance from the source, although here I initialize my source as 0, but if this source would have been an input also, then I would have just removed this source itself. We will remove this entirely so as to show you the example when we will do the longest path in a directed acyclic graph. But here itself, I know I have just initialized my source as 0, although the source can also be passed in as an argument and you can start from that source itself. Cool. The distance, as you are starting from that source, the distance is actually a 0. You will simply go back and simply try on for every node in this order of topological sort. Now this order is actually stored in my stack. So until my stack is empty, I'll grab the top element and I will try to see, okay, if this element is actually visited or not. If this is visited already, so because if I want to use this element and relax its neighbors, so which means I'm using this element, which means I'm using me. If I'm using me, I should have been actually relaxed already. Best possible relaxation. So I'm just saying, okay, I should not be int max because I'm initializing with int max itself, which is 1e9. It's not actually int max, but yeah, I'm just initializing with a very high value. So if I'm actually a high value, which means I have not been relaxed. If I have not been relaxed, please don't go and relax my neighbors, because for sure, if I was out of this picture, so my neighbors are also out of this picture. Please don't go and relax them. Now, why Aryan White is not important? Like, let's say, okay, if you're not visited, which means if you are very high value, so your neighbors will also be very high value. So there would not be any issues, right? Relaxing your neighbors, because if you are high, your neighbors will also be a high value because you are adding edge weight on them. But if this is a high value, if you add a very high value to a high value, it can actually overflow and result in a low value. So there can be a chance you are high, edge weight is high, the resultant me, which means my weight is high, edge weight is high, addition of them can actually result in a low value because of overflow itself. So it is good that you should not jump on if the value is already high. That is the reason I just put in condition, okay, if the value is already high, please don't go and relax its neighbors, because relaxing will actually result in an overflow, which will result in a minimum value, which I don't actually want because it is not a minimum value actually. Or if you don't want, you can actually have long and it will actually solve it. Cool. Now what I have to do is relaxing, which means going on to its neighbors and seeing, okay, if my weight plus the weight of this edge, if it's actually less than the weight or the value this my neighbor had, oh, I'll simply go and relax my neighbor, and I'll keep on doing it until my topological sort is empty. If it is empty, ultimately for every node I will have the maximum, I'll have the minimum distance to every node. And I know in the problem itself it was stated, okay, if the distance is actually not reachable, so please put it as -1 for that node. So if it is 1e9, which means it was not reachable. Now if it is not reachable, I'll just simply push in a -1 for that particular node, and ultimately I can just return a distance. And that's how in just simple O of n plus m, which is nothing but vertices and edges, you can simply get this solved. Now why this? Because of simple topological sort, because the complexity of simple topological sort is also a simple O of n plus m. And space is also O of n plus m, building a graph, building a distance array, and building a stack. Why stack? Using a topological sort, why distance? To bring in the answer for every node, which means the minimum distance from source node to every other node. And that's how you can simply solve this problem. I hope that you guys got it. The entire intuition of why we are actually, that's the reason I build specifically from intuition and then go forward, because building intuition is actually, that is useful. Many people just go, okay, I'll just teach the problem, explanation, then code, and then intuition. That's a bullshit, because in the problem, in the exam, in the interview itself, You will not start, okay, I'll just show you the problem, I'll show you the explanation, and I'll show you the intuition. No, it's actually the intuition, then explanation, then code. Cool. I hope that you got it. C++, Java, and Python codes down below. See you in the next video. Bye bye.